Okay, so in our problem, we have a square. We obviously know that a square means the two side lengths are equal, so they can both be represented as x here, and we know that our area of a square is going to be length times width, or so x times x, which gets our area to be x squared. What we also know is that x itself is a function of time. So that x, the side length, is changing as time changes or increases. And because of this, we also know that the area is also a function of time. So both side length and area are a function of time. So we can rewrite our area equals x squared as a of t is equal to x squared of t. Or another way to write that would be x at t squared. Okay, and so this is our relationship between area and side length. So this is the main equation we're going to use. So just to make sure we've done the stuff that he asked. So properly, clearly define the variable functions and other parameters, state the givens. So we know that our other givens are that x prime at t is equal to 10 centimeters per second. And we also are looking for the change in area when it is equal to 144 centimeters squared. So if our area is equal to 144 centimeters squared, and this is equal to x squared, then if we rearrange to find x, that means x is the square root of 144. X equals 12 centimeters. So this is also saying when the area is 144 centimeters squared, the side length is 12 centimeters squared. So another way we could write this is how is the area changing when the side length is 12 centimeters. The same problem. This is equivalent to the area is 144 centimeters squared. Same problem. And just let me freeze that. Okay, so we've stated our givens and we've clearly defined our variables. So now we will solve the problem. So the main relation that we have is a at t is equal to x at t squared. So if we take the derivative of a at t using the chain rule, we get a prime at t is equal to, and just restating the chain rule just in case we forget or just as a guide, if f at x is equal to g at x, then, f at g at x, if we have f at g at x, then we take the derivative, if this is y, y prime is equal to f prime at g at x times g prime at x. Okay, and so the derivative of this is we take the derivative of the outside, so 2, we bring it down, 2 times, we keep the inside the same, g at x reduce the exponent by 1. So this becomes 1. And then we multiply by, why am I doing that? Okay, this is x. Sorry about that. Let me just rewrite that. So a prime of t is equal to 2x at t to the power of 1 times x prime at t. Okay, so we are looking for a prime at t. We have 2, so let me just rewrite this. This is 2 times x of t times x prime of t. Okay, and it was when the area is 144 centimeters squared, which is the same as saying when x at t is 12 centimeters squared. So a at t equals 144 centimeters squared implies x at t is equal to 12 centimeters squared, or not squared. So we have our value here for x of t, and then the other variable here is x prime at t, and we know that x prime at t is equal to 10 centimeters per second. Okay, so we can sub these values in. So the change in area with respect to time is equal to 2 times x at t, which is 12, times x prime at t, which is 10, now we can just multiply this out. This is 2 times 120, which is 240. And that would be centimeters squared per second would be the unit. And so we can say that, when the area is 144 centimeters squared, the area is increasing by 240 centimeters squared per second. And that would be our solution to that problem. Are there any questions about that? Yeah. It's not asking for the time. Yeah, so it's just asking here for the speed. So we're just finding what is a prime at t. We don't actually know what x at t equals some question mark, right? So we don't actually know what's going on here. So if we wanted to sub in t, that would be difficult for us to do here because we don't have the entire relations for x at t and a at t. It's just looking for the rate of change, which we were given as 10 for the side length here. Any other, is that good? Cool. Any other questions? Okay, for some reason, this is being difficult. Okay, I will freeze this. Okay. Question 2. A toy hot air balloon is attached to a spool of rope that is 12 feet away from the balloon. 12 feet away from the balloon. when it is on the ground. The hot air balloon rises straight up. The hot air balloon rises straight up in such a way that the length of the rope increases at a rate of 5 feet per second. How fast is the hot air balloon? Rising at the moment the hot air balloon is at an altitude of 16 feet. And there is a graphic here. So we have someone on the ground who is holding that rope, or it's attached to the ground. There's a spool of rope here. There is a distance of 12 feet between the spool and the hot air balloon in the X direction, 12 feet. And this is the balloon. This length is increasing at 5 feet per second. And we don't actually know what this started as. Okay, so basically we have this. Take a moment to start to try to formulate that problem. Lots of times in these related rates, you're using relations, which basically, if you have your area, okay, how does the area relate to the side length? Well, we have the area is equal to the side length squared. There's a relation here because of the triangle. So go ahead and try to exploit that to find an equation, and you can use that to get to the answer to the problem. Okay, so our variable here is once again going to be time in seconds. T. And our functions will be L of t, and that is this right here. So that is the length of, sorry, no, that is wrong. This is L of t, because we're trying to find, or this is one of the equations. The length of the rope is increasing at a rate of 5 feet per second. So length of rope. And we know from the question that L prime at t is equal to 5 feet per second. And our other function is h at t, which is the height of the balloon. And we don't know about how this is changing, but we do know that we're looking for what is L at t, what is, how fast is the hot air balloon rising? So we are looking for h prime at t. What is h prime at t when h at t is equal to 16 feet, I believe it is. Yeah, 16 feet. So this is what we are trying to find. We don't know where h at t starts, which is fine. So we don't actually have the equation h at t. We don't know, there's no equation with t on this side, but we know that there's going to be a rate of change h prime at t. We don't know what that t value is either. That's the other thing, is that sometimes we don't need the t value, but we can still solve these questions, right? So obviously if we had the ht and some equation, we could just solve for that. But we don't. We just know we know how this is changing, and we're then determining how this is changing. Okay, so those are our givens. And so we can draw this out in another triangle. So we have h of t, 12, because this remains constant, and L of t. So we have that, just making sure. Okay. So what is our relation between, or we have a relation between these side lengths here, because it's a triangle, or right angle triangle is a key thing. And that is Pythagorean theorem. I'm gonna move this up a bit. So we have, that's once again, a squared plus b squared equals c squared. So we have 12 squared plus h at t squared is equal to L at t squared. Okay. And so we can do some implicit differentiation of both sides. And so if we do that, we are doing it with respect to t. So d by dt of 12 squared. Oh, sorry. D by dt of this whole left-hand side. So 12 squared plus h at t squared equals d by dt of L at t squared. Okay, and so since this is a plus in the middle here, we can just treat these as two separate terms. So what is the derivative of a constant? It is 0. So 0 plus, what is the derivative of h at t squared. Once again, we need to use the chain rule. So first we'll do this. So we'll bring the 2 down, keep h at t the same. The 2 becomes 1, and then multiply by the derivative of h prime at t is equal to, same thing here, bring the 2 down, L at t times L prime at t. Okay, and I'm just going to rewrite that on the next page. Okay. So we have 2 h at t, h prime at t equals 2 L at t, L prime at t. Okay, and so let's just think back to our givens. So once again, we know that we wrote them out here. So L prime at t is 5 feet per second. H at t is 16 feet. Oh yeah, it's 16 feet. Okay, and so one other thing, because it is a triangle, once again, is we have this is 12, this is 16, this is L prime at t. So we can use Pythagorean theorem here as well to figure out what L at t, sorry, not L prime at t, L at t will be when it's 16 feet high. So L at t squared is equal to 12 squared plus 16 squared, which will become 400. That would be 144, so this would be 256. 144 plus 256. L at t. So then squared. So that means L at t will be the square root of 400. L at t is going to be 20. Okay, so our last given here is L at t equals 20. And we are trying to find h prime at t. So if we look at our equation that we have here, we have something for this. We do not have something for this, but this is what we want. We have something for L at t, and we have something for L prime at t. So we're good to go. We have everything we need to solve this now. So let's go ahead and do it. So we have 2 times h at t, which is 16 feet. I'll keep the units in here. Then we have h prime at t, which is what we're finding, which is equal to 2 times L at t, which is 20 feet, and times L prime at t, which is 5 feet per second. Okay. And so just to make our units nicer, we can remove the feet from both sides. So we'll do that. And we want to rearrange for h prime at t. So h prime at t is going to equal to 2 times 20 times 5 feet per second divided by 2 times 16. And so we can, first of all, eliminate these 2's. So this will be 100 over 16 feet per second. We can definitely get a 4 out of that, then that'll be 25 over 4 feet per second. H prime at t. So when h at t equals 16, or the balloon is 16 feet above the ground, it is increasing in altitude by 25 over 4 feet per second. Any questions on that? Clear as mud? Okay. Freeze that. So exercise 3, our last one. Question 3. A large tank of water is in the shape of a cone. Assume the point of the cone is pointing downwards and is slowly leaking water. Is slowly leaking water at a rate of 3 meters cubed per hour. The base radius of the tank is 1 meter. We'll go here, 1 meter. And the height of the tank is 2 meters. So part A says, how is the depth of the water? Related to the radius, to the radius of the water's circular surface, of the water's circular surface. Does this relationship change over time? And B says, when the depth of the water is 1 meter, at what rate is the depth changing? And hint, the volume of a cone of height h, whose base radius is r, is V is equal to 1/3 pi r squared h. Okay, so once again with our previous questions, this one is broken up a bit just so you can build to get there. But we have a relation between the height, the radius, and the volume. All of them are changing with time once again. So time is our variable, and they're all impacted. All volume, radius, height are all impacted by that. So go ahead and build up the relation between these variables and go ahead and see if you're able to solve it like we did in the previous questions. I'll give you a moment or so just to make sure we have enough time to go through it, and then we will start going through it. Yeah. Okay, he must, so it says, sorry, 35? Ah, okay, he must have changed it then, okay. That was 35 centimeters cubed per hour. Oh, just 7. 37 per second, okay. Thank you. Okay, so we'll get started. Let me just freeze this. Okay. So. Okay, so the depth of the water changes with time. So d of t, that's the depth of the water. The radius of the water changes with time, d of t. And so we know we can look at a side profile of the, or this is the solution of part A. So let me just write that. So part A, once again, is how is the depth of the water related to the radius of the water's circular surface? Yep. Oh, sorry, no. R of T. Thank you. That'd be weird. Okay. So how does the depth relate to the radius of the circular surface? So if we look at a side profile of the cone, essentially what we have is if this is the water surface, then this is R, and this is H, and this is the hypotenuse of that. Okay? This is a right angle triangle. And obviously there's the other half of the water over here, but we're only looking at one half because we're using the radius. And so there's some angle here. Okay. So we can use our trigonometric relations here. So we have tan of theta is equal to the opposite over the adjacent. Okay, and yeah, that starts over there. So our height here, or our depth, right? The height of the water is the depth of the water. Okay, and so we have the opposite of this angle is the radius. And here we have the depth. And so at the start, our initial, so let's say the cone is full, then our triangle becomes same theta. This is going to be 2 meters. And this is going to be 1 meter. And I'll put the units in there because the rate is in centimeters. Okay, and so that means we get radius is 1 over 2. So that means throughout the entire time, our radius over our depth is equal to 1 over 2. And we can rearrange this. That means the depth is equal to 2 times the radius. So this is our relationship between depth and radius. So the first part, how is the depth of the water related to the radius of the water? The depth of the water is 2 times the radius of the water. Okay. So that is our answer to part A. And this relationship remains constant. And that's because if you were to see this go down, so let's say we had our full triangle, and if that's there, there's this theta. If the water comes down, it's now here. And so the radius has changed, and so as the height has remained the same. So that's why we can use this tan here. Okay, so that's A. Part B is saying when the depth of water is 1 meter, at what rate is the depth changing? Hint, the volume of the cone at height h, whose base radius is r, is v equals 1/3 pi r squared h. So we have v is equal to 1/3 pi r squared h. We've already discussed how d and r are functions of time. We've also discussed how the depth is equal to the height. So we can go ahead and do that replacement. So V is equal to 1/3 pi r squared d. And obviously the volume of the water is also a relation of time. So V of T, volume of water at time T. Okay, and this is our relation relating these variables. One other thing we have is that D is equal to 2 times R. So we can, we'll add in the T's here. So V at T is equal to 1/3 pi R at T squared. D is equal to 2R. So 2R at T. And we can combine that. So V at T is equal to 1/3 pi. Then this is R at T cubed, and this 2 will be placed up here. So 2/3 pi R cubed. Okay, and so now we take the derivative of this. So we have V prime at T is equal to 2/3. The constants stay around. Bring the exponent down, times 3. R at T, reduce the exponent by 1, multiply by the derivative of the inside. Wait. And the depth of the water is 1 meter. No, we don't want to replace it with R. Sorry, my bad. We want to go the other way. So we want to replace R with D, not go to R. That was silly. Okay, let me. My bad. Okay, I'm sorry about that. Okay, so I will screenshot this. Okay, so we have V at T is equal to 1/3 pi R squared D, 1/3 pi R squared D. And we have the relationship that D is equal to 2R. D is equal to 2R. And so we can replace R is equal to D by 2. So let's do that replacement. V of T is equal to 1/3 pi D at T over 2 squared times D at T equals 1/3 pi. We bring this in and take this out. So this will be D at T cubed over 4, which is equal to 1/12 pi D at T cubed. And then we take the derivative. V prime at T is equal to, keep the constants around, 1/12 pi times 3 D at T squared times D prime at T. And if we just combine this, that would be 1 pi over 4 times D at T squared D prime at T. And D prime at T. Okay. And so it is asking, when the depth of the water is 1 meter, at what rate is the depth changing? So when the depth D at T is equal to 1, what is D prime at T? Let me just, I do understand if you have to go, these will go.